Hi. So if you haven't seen my previous group theory lecture, then you can check it. Okay. So in this video, let's talk about the symmetric group. Okay, so this should be a easy video. So symmetric group, just some introduction. Okay, basically called a permutation group. Okay, so suppose S is a finite set, so it has an element. Let's say you get x1 up to x2 up to xn, and usually you can define a map, which phi is a S to S, 1 to 1, and onto map. So basically, phi is just a permutation. S. So basically, for example, phi can map from x1 to x2, x2 to x4, x4 to x5. Okay, but this writing symbol is cumbersome, right? So people like to write as so x1, x2, xn, and then you just map to xi1, xi2 up to xin. Okay, but this is still cumbersome, so we can reduce this to 1, 2, 3, n, and i1, i2, in. And these are just a permutation of S. Okay, so for example, phi can be written as suppose you have 1, 2, 3, 4, 4, 3, 1, 4, 3, 1, 3. So this map 1 to 2, 2 to 4, 3 to 1, 4 to 3. Okay, and suppose we have theta like let's see. So let's see. Yeah. So let's define. Let's maybe do some exercise. Okay. So exercise, for example, if psi is 1, 2, 3, 4, 1, 3, 2, 4, and our theta is 1, 2, 3, 4, 3, 1, 2, 4, and then we want to compute the psi theta. So it's 1, 2, 3, 4, 1, 3, 2, 4, 1, 2, 3, 4, 3, 1, 2, 4. Okay, so this calculation usually has two conventions. So one is from left to right. So I usually use it. So one map to 1, one map to 3. Okay, so one should map to. Yeah, so let's see. So one, let's see, right? So one map to 1, one map to 3, right? So it's 3, and the 2 map to 3, 3 map to 2. So 2, 3 map to 2, and 2 map to 1. So 1, 4 map to 4, 4 map to 4. So this is this. And then that's you can also calculate theta phi. So theta phi is basically 1, 2, 3, 4, 3, 1, 2, 4 times 1, 2, 3, 1, 2, 3, 4, 1, 3, 2, 4. Okay, so from here 1 to 3, 3 to 2. So 1 map to 2, right? And 2 to 1, 1 to 1. So 1, and 3 map to 2. 2 map to 3, so it's 3, 4, right? So you see there are different. Yeah, so this is just some convention, stupid convention. Okay. Okay, but we can discuss more detail of the structure. So let's set S is set, right? So with that AS to be the group, right? Basically, it's just all the phi, all the collection of phi. Okay, and then we pick an element called theta. Okay, so let's define an equivalent class. So we say that if A two element A, B belongs to S, if we say that A is B modulo theta, means that if this is just definition. So we say if A, B belongs to S, we define A is B modulo theta, means that B is A theta I for some integer I. So this means that you have two permutations, and such permutation can be done with by the theta power, some integer power. Okay, so claim A, B is an equivalence relation. So equivalence relation. Okay, so the first proof, the proof is A just a theta A because A is just A theta 0, which is A identity. The second is that if A is a theta B, and B is A theta I, right? So you can just write A is B theta minus I. So which tell you that the B is A theta. Oh, sorry, theta A. Theta A. Okay, so third is simple because A is theta B, B is theta C. So B is just A theta I, C is just B theta J. So combine these two, right? So you get C equals to A theta I plus C. Okay, so it's a equivalent relation. Okay, so let's define an equivalent. So if we have the equivalence relation, so we can take a representative, right? You can take a representative. Okay, so then these representative are called orbit. So orbit means that yeah. So equivalent class. So we can take a representative that's called small s, and orbit is defined to be the theta I, right? So I from 0 to 1 and keep going. Okay, so this is called orbit. So given an equivalent class, we can ask orbit. So basically orbit are which element is the same as falls into the same equivalent class. Okay, so yeah, you get theta, s theta 1, s theta 2, keep going, right? And but by definition, you know theta must go to identity because it's a finite group. So you get theta I minus 1. Okay, where is it? So this is the usual representation. Okay. Yeah, so yeah, this is the one classification, representation. Okay, so let's work on some examples. So your theta is 1, 2, 3, 4, 5, 6, and we want to write down another representation of how to write theta. So this is the usual representation. Another representation is that one can view that this theta only permutes to 1, 3, and permutes 4, 5, 6, right? So sorry. Yeah, so one can write this theta. One can write this theta. Sorry, the 3 is fixed, right? So it permutes 1. It permutes 1 and 2. So one can write theta as another representation is called 1, 2. 1, 2 means that 1 to 2, 2 to 1, and the 3, and this is 4, 5, 6. So 4, 5, 6 means that 4 go to 5, 5 go to 6, 6 go to 4. Okay, so now from this orbit representation, and each theta has this small representation, which is only contains a small bracket. Okay. Yeah, I mean, you can try a large example. So for example, well, let's maybe try something harder. Okay, so let's see. Suppose our theta is a representation, right? Is 1, 3, 4, 2, 6. Can you change into the common, can you change into this representation? So let me see. Suppose that we get it's 9 elements, right? And then the only proof that 1 to 3, so 1 map to 3, right? And 3 to 4, 4 to 2, 2 to 6, and 5 is fixed, right? And 6 to 1, and 7, 8, 9 are fixed. Okay, so this is just some small exercise to change the, yeah, so this means 1 to 3, 3 to 4, 4 to 2, 2 to 6. Yeah, so now we have 2 representation of the permutation group. So these are the 2 common representations. So 2 common representation of the permutation group. Ooh, should not be so difficult. Okay, you can try. Okay, so now let's talk about another subgroup, which is really important, called the alternating group. Which is an Sn. Okay, so this Sn means that the permutation of n letters. So you can view this S, which S is just n. Okay, so in order to start from this, let me just give some motivation. So let's consider we have a n-dimensional n-variable polynomial such that which there are all real numbers si minus xj. So I consider that just this. So for example, if p x1 x2 just x1 minus x2, if you get 1, 2, 3, you get 1, 2, 1, 3, 2, 3. Okay. Okay, now I want to that x as an act on this p. Okay, so acting on just change that let's say we pick on theta, right? So we be acting on, so we get x theta 1, theta n. So just permute this, okay? Oh, it's clearly that since it permute these two, right? So it's clearly this just become plus or minus px1 up to xn. Okay, so for example, let's check for example. Okay, so example, if in let's say you just theta to be 1, 3, 4, and 2, 4, 2, 5, and we act on S5. So let's check it. Right, so our x1, x2, x5 will be, let's say, x1 minus x2, x2 minus x3, x1 minus x4, x1 minus x5, x2 minus x3, and x2 minus x4, x2 minus x5, and x3 minus x5, and sorry, this is, I choose s4, s3 minus x5, x4 minus x5. Okay, so let's check let's check what's the results. So I change 1 to 3, 3 to 4, right? So this p after permutation, the 1 to 3, right? 1 to 3, so it's x3 minus x5, and the 2 become 5, so x3 become 4, and 2 become 5, yeah, 2 become 5, and the 3 become 4. Yeah, so you get yeah, let's see. So yeah, you can check it. Oh, it's very boring. I mean, just a stupid exercise. Okay, but what I just claimed that this p after permutation will be minus p. Okay. Okay, so that means let's talking about so now so it's not difficult to, it's not a little bit difficult to see what hell is plus or minus, right? Because hard to remember how to get the results, right? But let's give a notice. So we have noticed that if theta is called a transportation. Oh, sorry, so it's not transportation, no, transposition. Sorry, I'm stupid. So transposition position means that theta is just a b. So that means I just change a to b, b to a, right? So if you only change a to b to a, right, then your xi minus xj term. If ij act on these two, right, it must give some minus term. So that means if you have a transposition, then your p must go to minus p. Okay, so easy representative. Okay, so the result is that if your theta can be represented as the product of the transposition, and if the number of the products is even, then it's just 1. If the number of products is odd, you give me -1. Okay. Okay. And obviously that if you have two even permutation, their product will be even, right? Because the number of product just added. And if you get the two odd, it become even. And the odd even become odd, odd even become odd. Okay. So since if you have theta A times theta B, then the number of the transposition will just become the number of transposition on A plus transposition on B. Okay, so the rules is basically the odd plus odd, even plus odd, odd, even plus even is just even. Okay, so this is just a Z2 group. Okay. Yeah, so basically, yeah, just this is just from trivial observation. Okay. So let's define. So let's define a subset an in Sn. Basically, an is defined to be all even permutation of Sn. So basically, you can view that an is just all the permutation such that we'll fix p, we'll fix that polynomial p. Okay. Yeah, this is called the alternating group. Okay, so this group is very difficult and contains some very interesting results. Okay. Okay, so let's prove the first idea. Okay, so first trivial the first result is AN is not just a subgroup, A is a normal subgroup in SN. So normal subgroup. Okay, so there are various ways to prove it. The first way is that you can check it by your exercise. If you know the index of the AN is just 2, then it becomes normal. So any subgroup with index 2 must be normal. Okay, so this is the first way to prove it. Okay, so suppose you don't let's see. So suppose you don't know what I'm talking about. Right? You can define a W to be -1 and 1 and -1 and just use the product. Right, so W is a group. So this is obviously isomorphic to Z2. Okay. A abelian group, right? Cyclic group of order 2. And you can define a psi from your Sn to W. Just psi S is 1 if S is even. Psi of S is -1 if S is odd. So psi is homomorphism, right? Because the rules. Since we know that the rules is that even goes even, odd goes to odd times even times even is even times odd is odd, right? So basically it's a homomorphism. Or homomorphism, okay. So since it's homomorphism, so we can use the theorem, right? This theorem tell you what? Tell you what? So by definition, what's kernel, right? The kernel is just Sn. So by definition, your kernel modulo the An will isomorphic to image, which is onto, right? So it's basically W. So you get your An is basically contains a half order. So N factorial divided by half. So this tells you that An is a normal subgroup. So basically it's the same. You need to use the fact that index 2 subgroup must be normal. Okay, so suppose yeah, so that's maybe final remark. So if you don't know this proof, then I can prove to you. So if you have finite group and your H contains the N divided by 2, which is H is a subgroup of G, then H is normal in G. Okay, so in order to prove H is normal, right? So remember, normality means that X inverse. So X inverse must be H, right? So, okay, so let's see. Let's say if X belongs to H, then what is XH? So SH must be XSA must be H, right? Because X belongs to H. So if XH must be H, X inverse must be H. Okay. So if X is not the same as H, then what is SH? So XH cannot be H, right? And actually XH is another coset. So must be G. The G deletes all the H part. So G just put 2 parts, right? This is H. So XH must be this part if X is not in H. But it's the same argument for HX. So HX must be the same, must be also this part. So G quotient H. So they are the same. Okay, so which is H is normal in G. Okay, so this is just so I should say it's just some stupid appendix. Okay, so see you guys in the next videos. Hope you guys subscribe to my channel. Bye bye.